Good morning to all. Today we are going to discuss about the topic Laplace Transform. It is a type of improper integral. In the last module we have discussed about the integral calculus, that is beta and gamma function, which deals about the improper integration. So now we are going to deal about one type of improper integral which is known as Laplace transform. First, let us define the Laplace transform of a given function f of t. First, let f of t be a function of t defined for all t greater than or equal to 0. Then the Laplace transform of f of t, which is denoted by L of f of t, is defined by L of f of t is equal to integral 0 to infinity e power minus st f of t dt, and it is also denoted by the notation capital F of s. So from this definition we observe that this Laplace transform defined for the function which have domain only non-negative real numbers. Next we will discuss about what about the piecewise continuous function. So a function f of t is said to be piecewise continuous in a closed bounded interval, that is a comma b, that is a less than or equal to t less than or equal to b, if the interval can be subdivided into a finite number of intervals in each of which, that in each subinterval the function should be continuous and it should has finite right and left hand limits and both should be equal. Then we will move out to the definition of exponential order. What does it mean? A function f of t is said to be of exponential order if limit t tends to infinity f of t is a finite quantity, that is it should be a finite real number whenever a is greater than 0. Now let us move on to some properties of Laplace transform. So from the definition of Laplace transform we observe that it is a type of improper integral. Improper integral means the limits is from 0 to infinity or minus to infinity. So this is a kind of improper integrals. So integrals having some certain properties. So by using that properties we are going to define some properties of Laplace transform. First one is the linear property. That means L of a times f of t plus b times g of t is equal to a times L of f of t plus b times L of g of t. So now we will see how will it be hold. Now let us see the proof. So L of a of f of t plus b into g of t, by definition here the function is nothing but sum of two functions, that is linear combination of two functions f of t and g of t. So that is L of a times f of t plus b times g of t will be by definition integral 0 to infinity e power minus st into the function a times f of t plus b times g of t into dt. Since integration satisfies the linear property, we can split the integral into two parts. That is, first integral will be a times integral 0 to infinity e power minus st into f of t dt plus b times integral 0 to infinity e power minus st g of t dt. We are taking a and b are outside because they are the constants independent of t. So we are taking it outside. Now we can observe the first integral, that will be nothing but, so a is outside and the remaining integral 0 to infinity e power minus st f of t dt is nothing but L of f of t. So second integral will be in the same manner, it will be b times L of g of t. So therefore L of, if we apply the L on the sum of two functions, we will the answer will be Laplace transform of sum of two functions. Next we will move to the next property of Laplace transform, which is known as change of scale of property. That means if you change the scale as t goes to at, then the Laplace transform f of s will also having some transformation. What is that? Let us see the statement. If L of f of t equal to capital F of s, then L of f of at is equal to 1 by a times f of s by a. Now we will see the proof of this property. By the definition of Laplace transform, we have L of f of t is equal to integral 0 to infinity e power minus st f of t dt. We already seen in the definition this is nothing but capital F of s. Now let us take this as equation number 1. Now let us change the t as at. Then L of f of at is nothing but by definition integral 0 to infinity e power minus st f of at dt. Now let us go into substitution method. What is that? Let us take that at as some x, some variable x. Then what is t? T is nothing but x by a, and dt is nothing but dx by a, because a is a constant. Now we substitute this in this integration. We get integral 0 to infinity e power minus, in the place t we are replacing s by x by a. So it is nothing but e power minus s x by a into f of x into dt is nothing but f of x by a. So which is equal to L of f of x. Now we will observe that this 1 by a is a constant. So we will take that outside. So 1 by a integral 0 to infinity e power minus s by a into x f of x dx. Now we compare this with equation number 1, when we can observe that this is nothing but Laplace transform of constant s by a. So therefore L of f of t is nothing but 1 by a times f of s by a. So here integration is independent of variables. If we replace x or t, we get the same answer. So L of f of t is equal to 1 by a times capital F of s by a. So this is change of square of property. The next property is first shifting property. That is, if we shift that function by some exponential function, for example if e power minus at like that, then the resultant will be that capital F of s becomes f of s plus a. So this statement is like this: if L of f of t is equal to capital F of s, then L of e power minus at into f of t is equal to capital F of s plus a. And the second property is nothing but, if we multiply the function by e power at, then it is nothing but capital F of s minus a. First proof of the first property, that L of e power minus at f of t will come from the definition of Laplace transform. So by definition it is nothing but integral 0 to infinity e power minus at into e power minus st into f of t. Because in the definition we are having e power minus st, in the place of f of t we are going to substitute e power minus at into f of t. So this is nothing but integral 0 to infinity. We are taking the exponential in one side, and we can having one formula. What is that? A power m into a power n is equal to a power m plus n. So now we are going to use that property. So in that property, it will becomes, this integral will become integral 0 to infinity e power minus times a plus s into t f of t dt. So by comparing this with equation number 1, we can see that this is nothing but capital F of s plus a. That is, in the place of s, we are having the constant s plus a. So L of e power minus at into f of t is equal to capital F of s plus a. So next property. So L of e power at into f of t, as in the equation number 1, it will becomes integral 0 to infinity e power at e power minus st f of t dt. Here we have to observe only one thing, that is, here a having only plus sign, plus at. So we have to take, if we combine this, we will have e power minus st plus at. So we are taking minus sign outside. So this integral will become integral 0 to infinity e power minus of s minus a into t f of t dt, which is nothing but by definition capital F of s minus a. So therefore, if we shift the function by e power at, it will go to the function f of s minus a. So this is the shifting property. Next we will see Laplace transform of derivatives. That is, if we apply the Laplace transform to the derivative of the function, what will be the answer? So it is nothing but L of f dash of t. F dash of is nothing but first derivative of f with respect to t. So L of f dash of t is equal to s times L of f of t minus f of 0. So f of 0 is value of the function f at the initial point 0. Because we know that the t starting point is 0 to, from 0 only it is starting, that domain is starting. So therefore, the 0 is considered as an initial point. So now we will see the proof of this property. So L of f dash of t, by definition what will be? It is nothing but integral 0 to infinity e power minus st. In the place of f of t, we have to substitute f dash of t. So it is nothing but e power minus st into f dash of t dt. Now we are going to apply the integration by parts rule. Now in the last module itself, we have discussed about this parts rule, that property. What is it? It is nothing but integral u dv is equal to uv minus integral v du. Here what is u? Here we are taking u as a some e power minus st. Then what is dv? dv is nothing but f dash of t into dt. So to get back v, we have to integrate dv with respect to v. Then we get v of t is equal to, if we integrate f dash of dt, what will we get? We will get f of t. So the first term will be uv. So u is e power minus st, v is nothing but f of t. So we have to substitute the limits 0 to infinity. In the formula uv, the first term, next term will be minus of integral v du. So what is v? V is nothing but f of t dt. What is u? U is nothing but du. Du is nothing but derivative of u. What is the u? Here u is e power minus st. What is its derivative? E power minus st's derivative is e power minus st into, here the variable is t, constant is minus s. So it will come outside. So minus s into e power minus st. So into f of t dt. So therefore this will becomes first term. If we substitute c infinity, we know that as t tends to infinity, e power minus st tends to 0. So first term will become 0. The next term, if we substitute, and also we know that f of t is a function of exponential order. So as t tends to f of t will be some finite number. So infinity is finite number, it is a finite number, it is 0. Next, if we substitute 0, what will we get? F of 0 is nothing but, we don't know the value, so we are taking that f of 0. But what is e power 0? Anything power 0 is 1. So in the lower limit it will be minus times f of 0. This is now concentrate on to the integration. What is that? If we take that minus s outside, why we are taking that outside? Because it is a constant. So if you take minus s outside, it is nothing but minus into minus plus. So plus times s into integral 0 to infinity e power minus st f of t dt. Now we know that what is this integration? It is nothing but a Laplace transform of f of t. So therefore this will become minus f of 0 plus s times L of f of t. So therefore this L of f dash of t is nothing but s times L of f of t minus f of 0. Now we are going to apply this property to get a Laplace transform of nth derivative of f. What is that? So Laplace transform of derivative of order n. N means any positive number. So L of f of t is nothing but capital F of s. Then L of f power n of t, that is f power n of t means derivative of f n times after n times with respect to t. So it is nothing but s power n L of f of t, that is nothing but capital F of s minus s power n minus 1 into f of 0 minus s power n minus 2 into f of 1 and so on minus f power n minus 1 of 0. That is here f power n minus 1 means n minus 1th derivative of f and the value of that derivative at the point 0. That is initial point. We can observe that this is nothing but a polynomial of degree n with respect to s. Okay, so now we will see the proof of this. This is just consequence of the Laplace transform of derivative with respect to first time. So that is, we know that L of f dash of t is nothing but s times L of f of t minus f of 0. Now we move on to the L of f double dash of t. What is that? It is nothing but the derivative of f 2 times and the derivative of f dash of t first time. So this is nothing but L of f dash of t the whole dash. So it is by the same equation number 1. This is nothing but s times L of f dash of t, because f of t is nothing but here f dash of t. So it will become s times L of f dash of t minus f dash of 0, because already I mentioned you that f dash is nothing but here f. Okay, so which is nothing but, which is equal to, again by equation number 1, if we substitute the value of L of f dash of t, that is nothing but what? S times L of f of t minus f of 0. Now we multiply the s outside into inside, we will get, which is equal to s square into L of f of t minus s into f of 0 minus f dash of 0. So this is nothing but L of f dash of t oda expression. Okay, so now we move on to the L f triple dash of t. What is that? It will be in the same procedure. We will get that s cube into L of f of t minus s square into f of 0 minus s into f dash of 0 minus f double dash of 0. So proceeding after n minus 1 times, we will get L of f power n minus 1. After that we will get L of f power n of t as the resultant, that is s power n of L of f of t, that polynomial. So now we will move to the Laplace transform of properties with respect to t into f of t. What is that? This property is sometimes known as multiplication by t. What is it? If L of f of t equal to capital F of s, then L of t times f of t, that is a function is multiplied by another function t, that what is that? Algebraic function, that is polynomial of degree 1, that monic polynomial without constant term, that is t. If we multiply that with f of t, then we will get L of t into f of t is equal to minus of d by ds of f of s. What is d by ds of f of s? Because f is a function with respect to s, that is, it is the first derivative of f with respect to s. So if we multiply the function with respect to t, then the resultant Laplace transform will be nothing but the derivative of the Laplace transform L of f of t. Okay, so now we will see the proof. So according to the definition, L of f of t is nothing but integral 0 to infinity e power minus st f of t dt, which is equal to capital F of s, that is denoted as equation number 1. Now let us differentiate this on both sides with respect to s. What will you get? The left hand side will be d by ds of the integration, integral 0 to infinity e power minus st f of t dt. That f of s becomes d by ds of f of s. Now we have to go to the differentiating the integration. So now we know that the inside integrand, that is e power minus st f of t, is nothing but a function which has a derivative. So we are taking the d by ds inside. Here there are two variables, s and t. So we are using the partial derivative because we are going to differentiating only with respect to s. No, so here t will be considered as a constant. So we are differentiating with respect to s. So we are taking the d by ds will go inside as dou by dou s, and dou by ds of e power minus st is nothing but minus t times e power minus st, because here s is the variable, t is the constant. So we have to be careful in this. So minus t only will be come outside. So this integrand becomes integral 0 to infinity minus t into e power minus st f of t dt. Here f of t is the function of t, it never have s, so it is also considered treated as a constant. So that's why it remains same. So this is nothing but, if you take the minus sign outside, which is nothing but minus 1, which is equal to minus of integral 0 to infinity t times e power minus st f of t dt. Here we will observe that this is nothing but Laplace transform of the function t times f of t. So therefore L of t into f of t is nothing but, if we take the minus to the left hand side, we will get minus of d by ds of f of s. So if we proceed this same integration, same differential process, we will get in general L of t power n into f of t, that is molic polynomial of degree n without constant term, that is nothing but t power n. So L of t power n f of t is nothing but minus 1 the whole power n d power n by ds power n L of f of t, that is nth derivative of L of f of t, that is capital F of s. Now up to this we will discuss about the multiplication of f of t by t. Now we are going to discuss about the integrals of Laplace transform. If we calculate the integration of f of t, then if we apply the Laplace transform, this is nothing but the Laplace form of the original function divided by s. That is, if L of f of t equal to capital F of s, then integral Laplace transform of integral 0 to t f of t dt is nothing but capital F of s by s. Now we will see the proof. Let takes that integral 0 to t a g of t dt as some g of t. Then if we differentiate that g of t, then it will be g dash of t, which is equal to, we know that if we differentiate the integral with respect to dt, it will be nothing but f of t. So g dash of t equal to f of t, and from the integration, if g of 0 is nothing but what? 0 to 0. So it will be nothing but 0, because lower and upper limit are same. If we integrate and if we substitute by fundamental theorem of integral calculus, it is nothing but 0. So therefore now we apply this Laplace transform to this function f of t, then we will get L of g dash of t is equal to L of f of t. So it is nothing but, we see the property, what is that? Laplace transform of derivatives. According to that property, L of g dash of t is nothing but s times L of g of t minus g of 0, which is equal to L of f of t. If we take this g of 0 into an account, it is nothing but 0. No. So therefore s times L of g of t is nothing but L of f of t. So L of g of t is nothing but 1 by s times L of f of t. We are taking the s out on the other side, because here h should be greater than 0. Now if we replace the g of t by that integral, we will get the answer. That is a Laplace transform integral 0 to t f of t dt is nothing but capital F of s by s. Now we will go to the next property. That is beginning we have seen that multiplication by t. Now we are going to see about the division by t. See, if L of f of t equal to capital F of s, then L of f of t by t, which is equal to integral s to infinity L of f of t into ds. That is L of f of t is nothing but capital F of s. So now we will go to the proof. So by definition of Laplace transform, it is nothing but integral 0 to infinity e power minus st f of t dt, which is nothing but capital F of s. Equation number 1. Now let us integrate both sides with respect to s. Already there is in Laplace transform, there is an integral, but it is with respect to t. We should be aware of that. So it is nothing but now we will get integral s to infinity L of f of t into ds, which is equal to integral s to infinity. Already there is an integration, that is the integral 0 to t power minus st f of t dt into with respect to ds. So first we are differentiating with integrating with respect to dt, then only we are integrating with respect to ds. Now we know that these functions e power minus st f of t are all continuous and integrable functions. So therefore we can use the change of order of integration property. So using that property, so we can shift to the limits, then we will get ds dt, then and the derivatives becomes ds dt and the integral becomes, first one will be 0 to infinity, the next one will be s to infinity. That inside integration will be calculated first. So therefore on changing the integration we will get this. If you integrate this, what will you get? Here e power minus st1 with respect to ds. F of t is independent of s. If you integrate e power minus t, what will be the answer? E power minus st divided by minus t. Again we are going to integrate with respect to s, not with respect to t, because here t is treated as a constant. First we are integrating with respect to s only. So we will get e power minus st. It is integration. So we will get the constant in the denominator. So will be divided by minus t. Now let us apply the limit s to infinity. So for the infinity we know that already I mentioned you that as t tends to s tends to infinity, e power minus st will become 0. So the lower limit minus of e power minus s by t. So minus into minus plus, so that it will becomes e power minus st divided by t. Now we observe that according to the equation number 1, we will see that this is nothing but Laplace transform of the function f of t by t. So thus L of f of t by t is nothing but integral s to infinity L of f of t into ds. Now using these properties we are going to solve some problems, that is some kind of improper integrals. Before that we have to calculate some Laplace transform, some kind of standard functions. What are those functions? First we will observe that we are going to calculate the Laplace transform of t power n, that is monic polynomial. So L of t power n, what is that? Here f of t is nothing but 1. Okay, so L of t power n is nothing but a gamma of n plus 1 by s power n plus 1. We can use the property of multiplication by t also. In that case, as I said before, f of t is 1. Otherwise we can use a proper definition of Laplace transform also. Let us see, move on to the proof of this using the proper definition of Laplace transform. So by definition of Laplace transform, which is nothing but L of f of t is nothing but what? Integral 0 to infinity e power minus st f of t dt. Now replace f of t by t power n. What will become? So L of t power n is equal to what? Integral 0 to infinity t power n e power minus st dt. So here also we are going to use the same integration by parts rule. So we have to decide what we have to choose as u, what we have to choose as v. So we can use the substitution method also. Here we are going to use the substitution. Sorry, I mentioned wrongly that we are going to use the substitution method. Okay, we can use either method, but also we are here properly. The substitution method is very liked by the students, so I am going to use that only. So let us substitute method. In the substitute method, I am taking as u as st. T is nothing but what? Then u by s. We are going to differentiate with respect to t. Here u is the variable and s is the constant. Okay, so dt is nothing but du by s. And also we have to aware of the limits. As t tends to 0, what will be u? T tends to 0, u also will be tends to 0. As t tends to infinity, u also will tends to infinity. So using the substitution method, this L of t power n is equal to integral 0 to infinity u by s the whole power n, e power st becomes e power minus u, that dt becomes du by s. So this is nothing but u power n, s power n into s, that is s power n plus 1 into e power minus u du. Now we observe that L of t power n is nothing but 1 by s power n plus 1 into integral 0 to infinity e power minus u, u power n du. So now we concentrate on the integration 0 to infinity e power minus u, u power n du. This is nothing but by definition of gamma function, which we discussed in the last module. This is nothing but gamma of n plus 1. So therefore L of t power n is nothing but gamma of n plus 1 divided by s power n plus 1. So now let us calculate the Laplace transform of the next standard function, exponential function e power at. So L of e power at is nothing but 1 divided by s minus a, where s is greater than a. That because if s is equal to a, what will happen? S is equal to a means s minus a is 0, because 1 by 0 is infinity, it is not a real number. So we should not allow that condition. So provided if s is greater than a, then s minus a will be positive. For that condition, we can calculate the e power at Laplace transform. So L of f of t is nothing but integral 0 to infinity e power minus st f of t dt. If we replace f of t by e power at, it is nothing but L of e power at is equal to integral 0 to infinity e power minus st e power at dt, which is equal to integral 0 to infinity e power minus of s minus a into t dt, which is equal to, the integration is nothing but e power minus of s minus a t divided by s minus a minus outside, because that minus of s minus a is the constant. So if you apply the limits as we said before, as s t tends to infinity e power, that exponential will become 0. So therefore this is nothing but 1 by s minus a. L of sin a t, what is that? L of sin a t is nothing but a divided by s square plus a square. So by the definition of Laplace transform, L of f of a t is nothing but e 0 to infinity e power minus st f of t dt. Here if we replace sin a t by f of t, then we will get L of sin a t equal to integral 0 to infinity e power minus st sin a t into dt. So this is by the standard formula of the definite integrals. It is nothing but a by s square plus a square. In general definition, this formula is given here, that is integral 0 to infinity e power minus a t sin bt dt is nothing but b divided by a square plus b square. Here b is nothing but a is nothing but s. So the formula becomes a by s square plus a square. Next we move to the calculation of L of cos a t. It is nothing but s divided by s square plus a square. So again by the Laplace transform, L of cos a t is nothing but integral 0 to infinity e power minus st cos a t dt, which is nothing but s divided by s square plus a square, because the general formula is integral 0 to infinity e power minus a t cos bt dt is nothing but a by a square plus b square. Here a is nothing but s, b is nothing but a. Now using these formulas, we are going to calculate the another standard function Laplace transform, that is L of sin h a t, that is hyperbolic function. It value is nothing but a divided by s square minus a square, that is provided s should be greater than modulus a, because if s is equal to a, s square minus a square will be 0, which is also problem. If s equal to minus a also, there is a problem, because if you square it, it will become a square only. So therefore we should condition that s should be greater than modulus a. So therefore if we substitute the properties of Laplace transform standard function, which are those L of e power a t and L of e power minus a t. So if you substitute that, we will get that L of sin h a t is nothing but L of, we know that sin h a t is nothing, can be expressed in terms of exponential function. What is that? Sin h a t is nothing but e power a t minus e power minus a t divided by 2. Now if we replace the sin h a t by this formula, we will get that L of sin h a t is equal to L of e power a t minus e power minus a t divided by 2. Now by the linear property of Laplace transform, this can be written as 1 by 2 times, we can take it outside, it is a constant. So L of e power a t minus e power minus a t can be written as L of e power a t minus L of e power minus a t. If we replace that L of e power a t by that formula, that is 1 by s minus a, e power minus a t is nothing but 1 by s plus a. If we cross multiply, then we will get this fraction is nothing but s plus a minus of s minus a, so minus s plus a. So s will get cancelled, we will get 2a in the numerator, denominator will be s square minus a square, because s minus a into s plus a, the famous formula, a plus b into a minus b, what? It is a square minus b square. So therefore according to the formula, denominator will become s square minus a square. So L of sin h a t is nothing but a divided by a square minus a square, provided s greater than modulus a. The final formula, that is L of cos h a t, it is nothing but s divided by s square minus a square, provided s greater than modulus a. What is the difference between the previous formula and this formula? The numerator only the difference, that is the previous formula we will get a in the numerator, here s will be the numerator. But the procedure is same only. We are going to apply the Laplace transform of L of e power a t and L of e power minus a t, which is in the presentation, and cos h a t is according to the hyperbolic function. Cos h a t can be represented in terms of exponential function as e power a t plus e power minus a t divided by 2. So again apply the linear property of Laplace transform. L of cos h a t is nothing but 1 by 2 times L of e power a t plus L of e power minus at. So again if you apply the formula of L of e power at and L of e power minus at, this is nothing but 1 by 2 times 1 by s minus a plus 1 by s plus a. So if we cross multiply, and we will observe that the numerator will become 2 times s, because a only will get cancelled. Denominator again the same formula, a plus s minus a s plus a becomes a square minus a square. So here also the provided condition is s should be greater than modulus a. So L of cos h at is nothing but s divided by s square minus a square. So from this module we observe that Laplace transform is a type of improper integral, and if we transform the functions cos at or sin at, it will become some other functions in terms of fractionals like this, anything, and we are going to use in the next module, using these properties we are going to calculate and solve some type of improper integrals. Thank you.